Welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 1 lecture. I hope you enjoy it. This is Chapter 4, Section 4, so 4.4. And here we'll be discussing something called concavity and the second derivative test. All right, so in here first let's talk about what concavity is. All right, so definition. So let f be differentiable on some open interval I. Right? The graph of f is concave upward, right, on I when f prime is increasing. All right. Similarly, the graph of f is concave downward on I when f prime is decreasing. All right. So let's see what we mean here. So we've got a couple of different ways, well, two different ways that we're talking about here. We've got the concave upwards and the concave downwards. So let's look at concave upwards first. Concave upwards. So let's say that I have this graph, right? Something that looks like this, right? In here, this curve is concave upwards because the derivative, right, f prime, is increasing. And recall f prime talks about the slopes, right? So the slopes are increasing. What does that mean? Well, look at this. If well, perhaps I should extend this over here. If I look at the tangent lines, here I have a negative tangent line. Here I still have a negative tangent line, right? It's just less negative. Then I have a horizontal tangent line, which means it's a slope of 0. Then we end up with positive slopes and more positive slopes, right? So that's what we mean here. The slopes are increasing, right? They're going from negative up to 0 up to a positive value. So that's what makes this concave upwards. For concave downwards, it's essentially the same idea, just facing the other way. All right, so this is going to be concave downwards. And in here, let's say that our curve looks like this. All right, that's concave downwards because let's look at this from left to right. What's going on with the slopes? Well, we have positive slope, positive but less positive, right? This could be like a slope of 2, but this would be like a slope of 1, slope of maybe 1/2, 0, and then negative slopes, and then more negative. All right, so the idea here is that we're going from positive slopes to 0 to negative slopes, so the slopes are decreasing. Whereas over here for concave upwards, we were going from negative slopes to 0 to positive slopes. All right, so this is increasing. The slopes are increasing. F prime is increasing, and over here, F prime is decreasing. Right? Recall the slopes. So now let's take a look at something here. Let's say that we had this function. All right, so let's draw this scenario. I really don't want it to be so censored. There we go. Let's say that in here we had a graph that looked like this. right? Um, and you know what? Let's exaggerate it even more. There we go. All right. Now in here, let's uh, let's see what we have. Let's say that this right here is f of x. All right. Um, let's note a few things here. In up until here or around here, the concavity on to the left of this line is all negative concavity, right? So concave down. And you know what? Perhaps I should be doing this in yellow still. That's not what I meant. And we're gonna do that in yellow. All right. So on this side, it's all concave down, whereas on the right side of it, it's all concave up. All right. Now, well, let's see. If I take a look at what the derivative looks like, well, the derivative of this, right, this is, if you think of this as being a cubic function, the derivative would be a quadratic function. And if I take a look at this point right here, and at this point right here, in other words, the relative max and min, well, that helps me figure out what the derivative of this might look like. Because, well, we have the slopes, they're positive, and they're going to zero, right? They're getting smaller. And then we're going to have negative slopes. So positive slopes, but they're getting smaller. So the blue is going to be positive values, but they're getting smaller. So something like this. Positive values, but they're getting smaller. At some point, they hit zero. There it is. They hit zero. Then they got negative slopes. Negative slopes. But then they become less negative because they're going to, so here we went from zero to negative slopes, but then less negative so that we can go back to zero. So at here, where it changes from being less negative, this essentially goes to zero because these are the slopes, right? This is the derivative, excuse me. And then after that, where this has a tangent line of slope zero, the derivative is going to hit zero. And there we go. That would be f prime. And well, now let's look at what f double prime looks like. So f double prime. Well, that talks about the derivative of the derivative, right? And in here, if we take a look, if we think about the slopes here, they're going negative to less negative because at one point they hit zero, and then to positive, and then more positive. So they start at negative, here they hit zero. So where they hit zero, its derivative is going to have a zero. So it will look something like this. All right? And there in red, that's f double prime. Right? So there visually we can see the relationship between all these, the function and its derivatives, right? So again, in this function, where we have over here being concave down and over here being concave up, well, that's because the slopes were decreasing. At this point, they have slopes of zero. Excuse me, no. At this point, the derivative has a slope of zero, but it's where this changes concavity and it starts going upwards, right? If you compare the f of x with its second derivative, the concavity is down, the concavity is negative. Look at this, the second derivative is on the negative values. On this side, the concavity is positive. Look at that, the concavity went to positive values. And here, the concavity changes, f double prime hit the x-axis. All right, so let's build from something that I just implied there for how to find the concavity. All right, and notice that I related f of x with its second derivative to find the concavity. or when I spoke about concavity there. So theorem, test for concavity. Let f be a function whose second derivative exists on an open interval. All right. If f double prime of x is greater than 0 for all x in that interval, then the graph of f is concave upward on that interval. Right? If the second derivative is greater than 0, then f is concave upward on that interval. If the second derivative is less than 0 for all x in the interval, then the graph of f is concave downward on I. Right? So again, going back to the what I was saying over here, concave downward, the second derivative is less than 0. Concave upward, the second derivative is above 0. All right, and again, that has to do with the fact that, well, the first derivative is decreasing. Excuse me, the first derivative is increasing in this region, right? They're going from negative to 0, negative to 0, and the first derivative over here in this region is increasing, right? They're going from 0 to a positive value. I'll make a note here. If f double prime of x is equal to 0, then f of x is linear and concavity. Hold on, so let me hold on. I want to rephrase that a little bit. If f of x is equal to 0 for all I, for all x in I, so for the entire interval, not just at a point, then f of x is linear and concavity does not apply. It doesn't make sense to talk about whether a line is curved upwards or curved downwards because it's not a curve. All right, so that's all that note is saying. All right, so let's do some examples. Let's figure out where some function might be concave upwards or downwards. All right, so determine the interval or intervals for which f of x is concave upwards or downwards. All right. So let's see. Here I'm going to have f of x is equal to negative x cubed plus 6x squared minus 9x minus 1. All right. And we want to figure out where it's concave upwards and downwards. And from our definition up here, we said that, excuse me, from the theorem up here, that test for concavity tells us that the second derivative has to be greater than 0 or less than 0 to figure out where it concave upwards or downwards. So the very first thing I should do here is figure out the second derivative. All right, so f prime of x would be negative 3x squared plus 12x minus 9. Therefore, f double prime of x would be negative 6x plus 12. All right, and now to figure out where this might be positive or negative, well, what I need to do is set this equal to 0 right? Because what we're going to do is we're going to compare it to 0, right? We're trying to compare it to 0, so let's figure out where it actually is 0. So we have negative 6x plus 12, which gives us, move the 12 over, divide by negative 6, x is equal to 2. So at that point, we need to test, see what happens. So here's 2. Now we're testing into the second derivative, right? To the left of 2, I can plug in 0. To the right of 2, I can plug in 3. So when I plug in 0 into my second derivative, negative 6 times 0 is 0 plus 12. It's positive. When I plug in 3, negative 6 times 3 is negative 18. Negative 18 plus 12, that's negative. So in here I've got concave upwards, and over here I've got concave downwards. All right. And by the way, another way to think of this is positive concavity kind of gives you a happy face. Negative concavity kind of gives you a frown. So positive, happy, negative, frown. I don't know. Anywho, in there, that's another way to think about that. So now, in here, what did we find? We found that this is concave upwards on the interval from negative infinity to 2, and then concave downwards on the interval from 2 to infinity. All right. Now, let's see what this, let's get a visual for what this actually looks like. All right. This graph, and notice that I'm giving you the visual at the end, because we didn't need to see what the function looked like to be able to answer these questions, right? So this function looks something like this. And perhaps I should have done that vertical line a little higher. I meant horizontal. All right, it looks like this. All right, where this point right here is at 2. So from the left of it, we were concave upwards, right? That's what we have over here. And to the right of it, we were concave downwards. Next example, B. So let's say here that I have f of x is equal to x squared plus 1 over x squared minus 1. And again, we're trying to figure out the concavity for this. Where is concave upwards and where is concave downwards? And, well, turns out we need the second derivative. So we got to take the derivative of this. All right, well, the first derivative. And actually, before I do that, I just want to keep in mind here that the domain is that x cannot be equal to plus or minus 1. That'll be important later. All right, now, f prime of x. The derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. All right, let's see. What can we factor out of that numerator? I can take it to 2x, so we have 2x times, and we're left with x squared minus 1. Hold on. X squared minus 1 minus x squared plus 1. All of this over x squared minus 1 squared. At that point, what else do we have here? Well, that 2x is still there. And inside these square parentheses or square brackets, we have x squared minus x squared goes away. Negative 1 minus 1 is negative 2. And we have this over x squared minus 1 squared. So in here, this becomes negative 4x over x squared minus 1 squared. All right. Now, that was just the first derivative. I need to find the second derivative. So here we go. I need to find the derivative of the first derivative. The derivative of the top, negative 4, times the bottom, x squared minus 1 squared, minus the derivative of the bottom, 2 times x squared minus 1 times 2x, right by the chain rule, times the top, negative 4x, all over the bottom squared. All right, so let's simplify this. What do we get? The bottom part is easy. It's just x squared minus 1 to the fourth. On the numerator, what can we do? Well, we've got x squared minus 1 squared and x squared minus 1. So we can factor that out. I see also a negative 4 and a negative 4, so we can factor that out as well. So let's, I'll color coordinate these. So here's a negative 4, and here's the x squared minus 1. Now, we're going to take out a negative 4, and we're going to take out an x squared minus 1. So what are we left with? Well, what are we left with? See, we took out this negative 4, we took out an x squared minus 1, so I still have an x squared minus 1 in the first part, right? Because it was squared, took one out. Minus this 2 is still there, this 2 is still there. So 2 times 2 is 4. So I'm going to have 4x. This x squared minus 1, we took it out, and then we took out the negative 4, but we still have this x. So actually, what we have there is negative 4x squared. All right? And from there, well, what do we get? We can take x squared minus 4x squared. That's going to give us, well, let's see. I'll go on the next line. And actually, before I do that, this x squared minus 1 and this x squared minus 1, they reduce, right? We end up with x squared minus 1 to the third. This negative 4 is still out here. And here, x squared minus 4x squared is negative 3x squared. And then we still have this minus 1. All right. So what we can do here is if I distribute this negative into there, we end up with 4 times 3x squared plus 1 over x squared minus 1 cubed. All right. So now, at this point, we say, well, what can we do here? We need to set this equal to 0, right? Because if you recall, what we're trying to do here is find concavity, find where it's concave upwards or downwards. So we need to compare the second derivative to 0. So what we're going to say here is, well, if I take 4 and I set it equal to 3x squared plus 1 over x squared minus 1 cubed and set that equal to 0, well, I have a fraction equaling 0. The only possible way for that to happen is if the numerator itself is equal to 0. But solving for x here, well, let's see what happens. Divide both sides by 4, subtract 1, divide by 3, I end up with x squared is equal to negative 1/3. But that's not possible, at least not with real numbers, right? And in this class, we're only concerned with real numbers. So this has no solution, no real solution. All right. So then what do we do? Because we were going to use that, whatever answer was from there, we were going to use that to test for concavity around it. Well, what we're going to say here is the domain. All right, let's think about this domain again. X can't be equal to those values. So we can still test around the domain. And in fact, that's exactly what we need to do. We need to test around the domain to see what the concavity is around there. All right, just because we didn't get anything out of this doesn't mean that we can't find the domain. So let's test around the discontinuities. So let's see what we have. I'm going to say this is f double prime of x. Now we're testing around negative 1 and 1. And to the left of negative 1, I'll test negative 2. Between those, I'll test 0. And above that, I'll test positive 2. And we're testing it into the second derivative. So this was the second derivative right here, right? So let's see what happens. And let's look carefully at the top before we start plugging anything in, right? Whatever I have here, I'm going to square it. So that's going to be positive. A positive times 3, that's positive. Plus 1, even more positive. And then times 4, even more positive still. So the numerator is always positive. So what we have here is the numerator is positive. And now the denominator, let's see. Denominator, we're plugging in -2. -2 squared is 4 minus 1 is 3 cubed 27. So positive. So overall, we've got positive concavity there. So positive concavity there. Plug in 0. Well, we already said that the numerator, irrelevant of anything, was positive. So all we need to do is plug it in on the bottom. 0 squared minus 1 is -1. -1 cubed is -1. So on the bottom I get negative. Overall, this is negative. So negative concavity. And now around 2. Let's see. Plug in 2. Well, again, the numerator was just 2 was positive, but if I plug in 2 on the bottom, 2 squared, 4 minus 1, 3 cubed, 27. So again, positive concavity, right? So we're still able to find where this is concave upwards or downwards, all right? So concave up, and we said the positive was on bottom, yeah. So concave up from -infinity to -1, and then again from 1 to infinity. And concave down, well, just between those two, from -1 to +1. All right. Now let's get a visual as to what we found here. And this is the actual graph of the function here. We're gonna have at vertical asymptotes at -1 and also at +1. And we also have a horizontal asymptote here of not of 0, sorry, of 1. All right. All right. So in here, this is what the function is. We end up with this, and then that, and then that. All right. And let's look at what we had found up here. We said positive concavity to the left of -1. To the left of -1, positive concavity. Between -1 and 1, we said negative concavity. Well, look at that, negative concavity. And then to the right of 1, positive concavity. So there it is, positive concavity. Right? Perhaps I'll write that. So this was positive concavity, negative concavity, positive concavity. All right. Next one. Actually, let's define something here. Definition. And this is for something called a point of inflection. It is also sometimes called an inflection point, all right? And in fact, in general, I do call it an inflection point, and I'll be abbreviating it IP, inflection point. So let f be a function that is continuous on an open interval I. Oh, that's supposed to say interval. An open interval I. And let C be a point in the interval. I should say just a point on I. If the graph of f has a tangent line at this point, C comma f of C, then this point is an inflection point of the graph of f when the concavity changes from upward to downward or vice versa at that point, right? So let f be a function that is continuous on an open interval I, and let c be a point on I. If the graph of f has a tangent line at this point, c comma f of c, then this point is an inflection point of the graph of f when the concavity changes from upward to down or vice versa. All right, so let's see what we have here. And I'll draw a couple of scenarios. We can have something like this. Right, and in here, at this point here, this point, it does have a tangent line, right? And it goes from positive to negative concavity. So there we go. That's our inflection point. All right. But there's multiple ways that this can look. For example, it can look something like this. And here, we're going from negative concavity to positive concavity. So that's our inflection point. And this has a tangent line, right? Another scenario. It can look something like this. Ooh, I was trying to draw in blue. There we go. And let's make that better. There we go. In here, this point has a tangent line, happens to be a vertical tangent line, but it's going from positive to negative, all right? So that's our inflection point, all right? Now let's see another scenario where concavity changes somewhere. But let's see that we have this here. Let's change this. Let's say that we have this function here. Notice here that here we're going from a positive concavity to a negative concavity, but there is no point right at this value where the concavity changes such that it has a tangent line. So in here, there is no inflection point. All right, there's no inflection point here. So even though the concavity does change. So in the last two examples that we did, visually speaking, let me see. Here, we were going from positive concavity to negative concavity. So that's an inflection point. It has a tangent line, right? But in the next example, we change concavities here and here, right? From positive to negative and then negative to positive, but there's no inflection points because there is no tangent line. All right. So let's get a theorem in here to tell us how to find the point of inflections. So theorem. And again, this is for inflection points. If c comma f of c is a point of inflection of the graph of f, then f double prime of x is equal to 0. All right, so it has to be a point that's defined, and at that point, its second derivative would be equal to 0. So that's what's going on in this first three cases. All right. At this point, the second derivative is 0. Second derivative is 0. Second derivative is 0 here. All right. But not on the last case here. On this last case, it just happens to be that we changed inflection. Excuse me, we changed concavity at an asymptote. So let's find some points of inflection. All right. So the instructions are find the inflection points and determine the concavity of the graph. All right. So let's say that I have f of x is equal to 1/2 x to the fourth plus 2x to the third. All right. So we're trying to find the point of inflection. So inflection point is for the second derivative. So to get there, I must first find the first derivative, right? So f prime of x would be 2x cubed plus 6x squared, right? Giving us that f double prime of x is 6x squared plus 12x. And now the inflection points. We said that that's where the second derivative is equal to 0. So we've got 6x squared plus 12x equals 0. If I divide everything by 6, I end up with x squared plus 2x equals 0. Factor in an x times x plus 2 equals 0, giving me my two solutions of x equals 0 or x equals -2. So in here, what we found is where the second derivative is 0, right? So now we must test around those points to figure out the concavity. So we've got -2 and 0, and we're going to plug that into the second derivative to see what's going on. Now in here, I'm just going to look at this as 6x times x plus 2, just to make it easier. In general, when we have things factored, it's much easier to evaluate. All right, there's less stuff to keep track of. Especially here where all we care about is the sign. All we care about is whether it's positive or negative, right? So let's test -3, -1, and 1. All right. So let's plug in -3. 6 times -3, negative value. -3 plus 2, negative value. Negative times a negative, it's a positive. So in here, we're concave upwards. Next one, plug in -1. 6 times -1, negative. -1 plus 2, positive. A negative times a positive, negative. So it's concave downwards. Plug in 1. 6 times 1, positive. 1 plus 2, positive. Positive times a positive is positive. So we got positive concavity there. All right. Now, this answers the first question of, well, actually the second question, the concavity of the graph, right? So this here, we've got, so concave upwards, we've got it from -infinity to -2, and then again from 0 to infinity. Concave downwards from -2 to 0. All right. And now as far as finding the actual inflection points, well, they're points. They're points in the graph. We know where the second derivative is 0, so all we need to do is plug those into the original function. And what does that give us? Well, that gives us the inflection points of, well, from this 0, we end up with the point, so let's end up with 0, right? 0, 0. And then from this -2, I end up with, if I plug it into the original function, I end up with -8. So now we can actually get a visual for this. All right, so let's see what the visual would look like here. This function looks something like this. Let's see. Yeah, close enough, right? Where here and here we've got inflection points. This is at -2, this is at 0. That's 0, 0. This is at the height of -8. And notice the concavities. Here it's a positive concavity, negative concavity, positive concavity. All right? Because of the way that they're curved. And perhaps I'll make this middle part a little bit more obvious. That's a little too much. There we go. All right. All right. So next one, D. Let's say that I have f of x being equal to x minus ln of x. And again, we're looking for concavity and inflection points. So we got to find the second derivative. So the first derivative would be 1 minus 1 over x. And the second derivative would be 1 over x squared, right? The derivative of 1 is 0. The derivative of negative 1 over x is positive 1 over x squared. So at that point, we got to say, well, we got to figure out our inflection points. And our inflection points, again, are where f double prime of x is equal to 0. So what do we get? Well, if I try to figure that out, I have 1 over x squared equals 0. But we know that a fraction is only equal to 0 whenever the numerator is equal to 0. But that doesn't make sense here, right? 1 can't be equal to 0, so no solution. Which tells us no inflection points. But that doesn't mean that we can't test for concavity, right? Because if you recall, we can still test for concavity by checking the domain. So let's figure out what the domain here is. The domain for an ln function, well, let's see, the domain for x, that's just all real numbers, so there's no issue there. The real issue is here with ln. The domain for ln is that its input must be strictly greater than 0. So that tells us what we can do. We can just test any point where x is greater than 0 into our second derivative. So, for example, we can test 1, and I'm going to test it into the second derivative. And when I plug in 1, 1 squared, 1, 1 over 1, 1, which is positive. So it tells me overall it's concave downwards. So in here, right, starting at 0, right? So starting at 0. So there's no inflection points, but we have that it's concave up on its entire domain. So from 0 to infinity. Now let's get a graph of this one so we have an idea of why this would make sense. This graph looks something like this, right? Right? Sort of similar to like a parabola, but it has this asymptote here in this region. At x equals 0, there's a vertical asymptote. But notice that it's concave upwards. It's positive concavity throughout the entire interval, all right? Throughout this entire domain, I mean. So next example, so that was D. E. So let's say that I have f of x being equal to e to the -3 over x. And again, we're looking for concavity, we're looking for inflection points, so we need to find the second derivative. The first derivative would be, well, the derivative of e to some power is e to that power, and then by the chain rule, times the derivative of the inside. The derivative of -3 over x is +3 over x squared. So I can rewrite this as 3e to the -3 over x over x squared. All right, so that's the first derivative. the second derivative. Well, let's see what that looks like. I need to do the quotient rule, right? I've got a quotient of two functions, so the derivative of the top. Well, look at that. That's very similar to what I had here. So it's just going to be, this 3 is still there, but now I need to take the derivative of this piece. So it's 3 times the derivative of e to the negative 3x, which is all of this, which is 3 e to the negative 3 over x squared. So that's the derivative of the top, times the bottom, x squared, minus the derivative of the bottom, 2x, times the top, 3e to the negative 3 over x. All of this over the bottom, squared. All right, so let's see what we can do here. Let's redo some things. Let's cancel things out. We've got this x squared and this x squared cancel each other out. We've got, well, that's it. Now, what else can we do? We've got this 3 and this 3 can be factored out, and perhaps I should have done it as this. This 3e to the negative 3 over x and this 3e to the negative 3 over x can be factored out. And what we're left with there would be, well, let's factor that out. The bottom's e's is just x to the fourth. The numerator, we're factoring out a 3e to the negative 3 over x, right? What are we left with? Well, in the first part, I'm just left with this 3, right? This 3 was not factored out. Anything else, well, that's it. Everything else was either factored out or canceled out. Minus, on this side, I'm left with a 2x, right? We took out that e to the negative 3x. At that point, that's our second derivative. So now, why do we want that? Well, again, we need to find inflection points, which are where f double prime of x is equal to 0. So let's set this equal to 0. 3e to the negative 3 over x times 3 minus 2x over x to the fourth equal to 0. And here, well, we have a fraction equaling 0. And in fact, let me rewrite this fraction even further, because this is really saying 3 times 3 minus 2x over x to the fourth e to the positive 3 over x equaling 0. So now, in here, I've got a fraction equaling 0, right? And the only possible way for a fraction to equal 0 is if the numerator itself is equal to 0. So this tells us right away that we're looking for where 3 times 3 minus 2x is equal to 0. Solving for x here, divide both sides by 3, move the 3 over, divide both sides by negative 2. I end up with x is equal to 3 halves. All right. So there we go. That is a point of inflection. That's the x value. As far as the y value is, well, we would have to just plug it in into the original function. So we need f of 3 halves, which would be e to the negative 3 over 3 halves. So in here I've got 3 divided by a fraction, which we know is the same thing as multiplying by its reciprocal. These 3's cancel each other out, so I get e to the negative 2. So our point of inflection is at 3 halves comma e to the negative 2. Now, as far as where this might be concave upwards or downwards, well, let's see. We've got our inflection point, so we have to test around our inflection point, but we must also test around the domain. And what was the domain here? In here, the domain is that x cannot be equal to 0, right? Because at 0, I end up with negative 3 over 0, and well, we don't like dividing by 0, so that's not good. So we have to test around 0, and we have to test around 3 halves. So let's see. So we have our number line. Here's 0, here's 3 halves. And there's absolutely no reason for me to be writing that big, or that spaced out. So we're testing things into f double prime. We're testing around 0 and around 3 halves. Okay. To the left of 0, I'll plug in 1. Between 0 and 3 halves, I'll plug in, to the left, I'll plug in negative 1. Between those two values, I'll plug in 1. And above this, I'll plug in 2. All right. So let's see. We're plugging this into the second derivative, right? And this was the second derivative right here, right? So let's see what we get. Well, first let's figure out what we have in the bottom. Irrelevant of what we plug in here on the bottom, this is always going to be positive. How come? Well, this part we're raising to the fourth, right? We're never plugging in 0, but any value that we're plugging in here is going to be positive, right? And then over here, e to any power is always positive. So this entire denominator is always positive. So what we really care about is what's going on top, all right? So when I plug in -1, 2 times -1 is -2. 3 minus -2 is 3 plus 2, which is 5 times 3 is 15. So that's positive, right? Because it's being divided by a positive, so it's just positive. Concave upward. Plug in 1. 1, excuse me. 2 times 1 is 1. 3 minus 2 is 1. 1 times 3 is 3. So we've got positive again. Positive concavity. Plug in 2. 2 times 2 is 4. 3 minus 4 is -1. 3 times -1 is -3. So we get negative, right? We already said that the bottom is always positive. So negative or positive is negative. All right. So that gives us our where we're concave up and down, right? So um, concave up would be from -infinity to 0, and then again from 0 to 3/2. And then it would be concave down from 3/2 to infinity. Notice here that I didn't say from -infinity to 3/2. All right, that would be wrong to say. Why is that wrong to say? Because in here it's implied that 0 is included, but 0 is not even in the domain, so you can't talk about what's happening as what the function is actually doing at 0, just around it, but not there. So in here that would be completely wrong to say. So that's what we had to. So we had to make sure that we put it as two different intervals. All right, so let's get an idea of what this function looked like, so you can see how this applied. Oh, I didn't want to do that. So here we go. We've got a vertical asymptote here at 0, right? That's not part of our domain, but we've got a vertical asymptote, and the function actually looks like this. This side it goes like that, and on this side at 0, from this side it's not going to be an asymptote, but it is a discontinuity, and it looks something like this. All right, positive concavity, negative concavity. This point right here is at 3/2, and at the height of e to the -2. All right. So there you go. Positive concavity to positive concavity, and then negative concavity. And that's the end of that one. Now, let's talk about something called the second derivative test. All right, this was we were speaking a lot about concavity, but we also must talk about the second derivative test. So theorem, the second derivative test. And in here, I really should be saying, or this really should be called second derivative test for relative max and min. All right, so that you understand that this is going to help us find relative maximum minimums. So let f be a function such that f prime of c is equal to 0. What is that really telling us? That's telling us that c is a critical value. All right. So the f of function says that f prime of c is equal to 0, and the second derivative of f exists. All right, exists on an open interval. Containing C. All right, so we're gonna have a few things here. First, if f double prime of x, if f double prime of C is greater than 0, then f has a relative minimum at C comma f of C. 2. If f double prime of C is less than 0, then f has a relative maximum at that point. And lastly, I'll say here, if f double prime of C equals 0, then the test is inconclusive. All right. If it's inconclusive, then that means, well, we gotta figure out things using a different test or different methods. All right. Or perhaps it's just not a relative min or a max. All right. It just happens to be a critical value. So let's see why this would make sense. All right. In here, let's look at the scenario number 1. We've got the second derivative at that point is greater than 0. But prior to that, we said that C is a critical value. So that means that the slope is equal to 0 at C. So let's get to the two possible ways that can look like. And I'll do them on the same graph here. Let's say that this was our function. All right. In here, we've got here around there, that will be our inflection point, right? We're going from positive concavity, from negative concavity to positive concavity, right? At this point, we've got a horizontal tangent line. There we have another horizontal tangent line. So these 2 points are critical values, right? In this first scenario, f double prime of C is greater than 0. Well, if what this is saying is, if the concavity is positive and at the point where we've got a critical value, then this is a relative minimum. Similarly, over here, this is saying if the concavity is negative at where we have a critical value, then we have a relative max. All right. So let's see what we can do with that. So this essentially gives us another way of classifying relative mins and max. All right. So now find and classify all relative extrema. So let's say that I have f of x is equal to x to the 4th minus 4x cubed plus 2. All right. So the very first thing I need to do here is, well, I got to find critical values, right? We got to find our critical values here. So I need to first find the first derivative, all right? So the critical values are essentially where the critical points happen, right? Which is f prime of x is equal to 0 or undefined. So f prime of x would be the derivative, which is 4x cubed minus 12x squared. All right, and to figure out critical points, I'm going to set this equal to 0. So I'm going to factor this. I'm going to say 4x squared times x minus 3 is equal to 0, right? And that tells me that either x is equal to 0 or x is equal to 3. From this first part, x is 0. From that part, x is 3. So there we go. We've got our two critical values. Now that we've got that, well, we can apply the second derivative test. And for the second derivative test, we need to find the second derivative. So right here, second derivative test. And that means we'll find f double prime of x. Going from this version, the derivative there ends up being 12x squared minus 24x. All right. Now, what we can say here now is, well, let's see. Let's factor this as much as possible. I can take out 12x and I'm left with x minus 2. So now applying the second derivative test. Okay, well, we gotta plug in our points. Well, let's plug in 0. F double prime of 0, so this is for x equals 0. F double prime of 0, well, 12 times 0 is 0. 0 minus 2 is negative 2. 0 times negative 2 is 0. Let's check what happens at 3. F double prime of 3 gives us 12 times 3 is 36. 3 minus 2 is 1. 36 times 1 is a positive value. In other words, it is greater than 0. Alright? We don't really care what the actual value was, it's just that it's greater than 0. So now let's look at what we had said over here about how to classify them. If we had being greater than 0 at our critical point, we know that it is a minimum. If it was less than 0, it's a maximum. And it's equal to 0, then it's inconclusive. So in here, the second derivative, where we got 0, this is inconclusive. But for this one, where we got positive, we got a relative minimum at that critical value, x equals 3. Right? Now, where it was inconclusive, well, what can we do? Well, let's see. We know other ways for finding or figuring out whether something's a relative max or a min, right? So what we can do here is use the first derivative test. And we need to test around our points between 0 and 3. But this time, we're plugging into the first derivative. So I'm going to check negative 1, 1, and 4. If I plug in negative 1 into our first derivative, well, let's look at our first derivative. Here it is, 4x squared times x minus 3. If I plug in negative 1 minus 3, that's negative 4. Negative 1 squared, positive 1. 4 times 1 times negative 4. Overall there we end up with negative, so it is decreasing. Plug in 1. 4 times negative 2, that's negative. So again we get negative. Plug in 4. 4 minus 3 is 1. 4 squared, that's positive. So 4 times a positive number times 1. Everything's positive there, so we get positive. So that's increasing. So in here, here we already knew that this was a relative minimum, right? We had already found that. And it makes sense, right? We go from decreasing to increasing. But here, well, it turns out that this is neither a relative max or min. All right, that's neither relative max or min. Now, let's get a visual for this. So this graph looks something like this. All right. I guess I can draw that a little bit better. Something like that. All right. And in here, well, what did we find? Well, here at 0, and here at 3, well, we've got our critical values. Look at that. That's not very vertical. And at those critical values, well, we already classify them to be, this one is a minimum. Well, yeah, right? Visually, we can see that now. And this one is neither. In here, and perhaps this graph should look a little bit more like this, a little bit more curved this way here, so you can see the change there. Let's see, yeah, that looks better. So in here, we've got, it has a tangent slope of 0. Whoa, didn't mean to erase. It has a tangent slope of 0 here, has a tangent slope of 0 there. So clearly those are critical values. But in this one, it's a relative minimum. This one is neither, right? We're going from decreasing to decreasing, so that's neither. But it is a point of inflection. Notice that here, we're going from positive concavity to negative concavity. And then somewhere in the middle over here, we change again from negative concavity to positive concavity. All right, let's do another one. Let's say that I have f of x is equal to x over ln of x, right? And again, the idea here is to classify the relative extrema. So we need to find first the critical values to figure out where the relative extrema are. So to do that, well, the critical points are where f prime of x is equal to 0 or undefined, right? So before that, let's figure out something here. I want to speak about what the domain is. The domain, well, we have a fraction here, right? So that means that that's where ln of x cannot be equal to 0. So this tells me that x cannot be equal to 1, right? Because ln of 1 would be 0. What else do I know? In here, because I have an ln function, I must have that x is greater than 0, right? So these two combined essentially tell me that my domain is, we start at 0, go all the way up to 1, and then go from 1 all the way up to infinity. All right, so all the positive values except for 1. All right, now, that's just something to keep in mind. So critical points, f prime of x is equal to 0. So in here, I must use the quotient rule, the derivative of the top, 1, times the bottom, minus the derivative of the bottom, times the top, all over the bottom, squared. And, well, let's see, let's reduce this a little bit. What we really have here is ln of x minus 1 over ln of x squared, right? And from here, well, to find our critical values, set this equal to 0, right? So we've got all that equal to 0, and we've got a fraction equaling 0. Whenever we have a fraction equaling 0, that can only happen when the denominator itself is equal to 0. So solving this, we end up with ln of x is equal to 1, therefore x is equal to e. All right, so that's our critical value. Well, maybe I'll write this over here. ln of x is equal to 1, which tells us that x is equal to e, and that's our critical value. All right, now, what do we need? Well, if we're going to be applying the second derivative test, we must find the second derivative. So f double prime of x, what would that be? Well, we've got a fraction, the derivative of the top, so that's going to give us 1 over x, times the bottom, ln of x squared, minus the derivative of the bottom, 2 ln of x times 1 over x, right? And that's from the chain rule, times the top, ln of x minus 1. All of this over the bottom, ln of x squared, squared. All right. so let's simplify this. Well, what do I see that we can factor out? I see that we have a 1 over x in both of these. I also see that we have an ln of x in both of these. So that's what we're going to factor out, and I'm going to color coordinate this. So now we have, I'm going to factor out a 1 over x and also an ln of x. And what this gives us now, well, what are we left over? I took out a 1 over x, I took out an ln of x, I'm left with an ln of x minus. I took out the ln of x, the 1 over x, I'm left with, I'm just left with 2 and this piece over here, right? But if I distribute that 2, well, we end up with negative 2 ln of x plus 2, right? And all of this over ln of x to the fourth. Simplifying this a little bit, well, this 1 over x, I can just put it as x on the bottom. This ln of x to the fourth and this ln of x, they just reduce to ln of x to the third. In the numerator, 1 minus 2, right, because ln of x minus 2 ln of x, that's negative ln of x, and then we have that plus 2. All right, so now that we've got that, let's see. We need to test our critical value, right? Our critical value was e. So what we need to do here is to apply the second derivative test. Second derivative test. So f double prime of e gives us negative ln of e plus 2 over e times ln of e squared. All right, let's think about this. Ln of e is 1. So what I really have here is negative 1 plus 2, that's 1. E times 1 squared, that's e. 1 over e is greater than 0, which tells us that we, in that region, we have a positive concavity. All right, so we once again have a relative min. All right. Now, as far as what this looks like, if I plug in e to the original function so that I can get a coordinate here, I get e over ln of e, so that's just e, right? E over 1. So in here, I can say that this gives me the point e comma e. All right, so let's go ahead and sketch this. We know that the domain was from 0 to infinity except at 1. So this is what our function looks like. At 1, we've got a vertical asymptote. And then from there on, the function looks something like this, right? Where this point right here is at e comma e. And look at that. It has a horizontal tangent line, right? That's why it's a relative minimum. And it has a negative concavity. Excuse me. It has a horizontal tangent line. That's why it's a critical point or a critical value. And it's got a negative concavity, which is what makes this a relative minimum. All right. So that would be the end of 4.4. Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.